Just so everybody knows, and I know you're not all seniors, but the seniors, you will be responsible for the section 6-1 homework because you're done on Friday. So 6-1 day 1 and 6-1 day 2, and then you're finished. Everybody else, we will have a quiz. It's actually not the last day of school, and that's in case anybody's gone and we have to do a makeup on the last day of school, but it's just on 6-1 and 6-2. That's what we're covering for the rest of the year. When you go to college, vectors, which is what we're going to start studying today, are often lumped together with matrices because vectors and matrices together can form a full semester-long course of math. But actually, it'd probably be more like a trimester of math. And part of what we're looking at has some applications of trigonometry, which might, scare you a little bit, but mostly what we're going to be doing is using the calculator to find some basic SOHCAHTOA stuff. I mean, that's a big piece of this. So we have this picture on here, and on the yellow it doesn't turn out too fantastic, but young salmon migrate from the freshwater they're born in to saltwater and live in the ocean for several years. When it's time to spawn, the salmon return from the ocean to the river's mouth, where they follow the organic odors from their home stream to guide them upstream. I always wondered how they found that out, that fish can smell in the water there. And researchers believe the fish use currents, salinity, which is the amount of salt in the water, temperature, and the magnetic field of the earth to guide them. And some fish swim as far as 3,500 miles upstream for spawning. So animals. I had mentioned before about, trying to figure out if elephants do talk to each other. Apparently, there's recently been some, big movement on that field. So lots of fields that are still wide open for study. What we should expect in 6-1 and 6-2, this reminds us about the uses for vectors in a plane, basic operations that we do with vectors, and we can use them to, well, you've done this in 9th grade science, for goodness sake. You've talked about work and using vectors for work. And we're going to talk down here specifically, and we won't necessarily get to all these things, but two-dimensional vectors, vector operations, unit vectors, direction angles, applications of vectors, the dot product, angles between vectors definitely, maybe not projecting one vector onto another, but we will talk a little bit about work. So vectors, what do they look like? Vectors are a way to represent motion, and what we have is, well, I'm going to flat out tell you this. This book doesn't write vectors like almost every other math book does. Vectors really should have a half an arrow. Do you see how that doesn't have the full arrow over here at the end? And that's to show the difference between a ray and a vector. This book definitely puts rays on absolutely everything. But our vectors are to show us the motion from, this is called the head of the vector, from the tail. So the tail is where it starts, and you use that geometry of, hey, this one has an arrow to show you this is the way it's going to go. So direction and magnitude is what vectors are going to show us. So we want to be able to apply the arithmetic of vectors. We're going to use the head minus tail rule. We're going to talk about magnitude today, do some vector addition and scalar multiplication. We're going to find a unit vector and resolve a vector. We'll start the steps of that. We'll definitely wait for the real world problems until tomorrow. We just want to get some basics of vectors today. So two numbers are all that it takes to represent both the magnitude of an object's velocity and its direction of motion. We simply look at ordered pairs of real numbers in a new way. We don't use parentheses. We use vector component notation. And it looks like kind of a smushed less than and greater than symbol. That's our vector notation. So we use that to represent a vector with its initial point at the origin and an arrow pointing to the ordered pair AB. So that shows this is going to be the motion, but it's just a representation. That's all it is. So here we have this point AB out here, and if we wanted to show that this was a vector, we could write a ray showing it's going in the direction of AB. So the point represents the ordered pair AB, and by putting a ray on there, we show a representation of a vector AB. Two-dimensional vectors. We're not going to go to the three-dimensional, four-dimensional vectors in here. Two-dimensional vector V, an ordered pair of real numbers, and this one is called component form. We're also going to see a different form, but component form is the most worked with form that we have. It's the easy way to represent it, vector AB. The numbers A and B are the components of the vector. So you have the horizontal component and the vertical component. The standard representation of the vector AB is an arrow from the origin to that point AB, trying to show that it's a vector. The magnitude of V is the length of the arrow. So length, we have to think, that should be distance. So I need everybody to make a little connection here to the fact that magnitude is just going to be the length, which is just the distance. And you've already studied the distance formula before, so not going to be new. So it is, the magnitude is the distance or the length of the arrow, and the direction of V is the direction in which the arrow is pointing. So that's where the trig comes in, where we try to say from our positive x-axis, what are we talking about for this angle? How much is it? And the vector 0, which is component form 0, 0, is called the zero vector. It doesn't have any length or direction. That's one of those things that has to be there in order for everything that we know about vectors to work. There has to be a 0, 0 vector. It's often convenient to represent vectors with arrows that begin at points other than the origin. The important thing to remember is that any two arrows with the same length pointing in the same direction represent the same vector. So just because the vector doesn't start at 0, 0 doesn't mean that there's not another vector just like it somewhere else. And here we have an example of those two. So we have vector RS and vector OP. The arrows for vector RS and OP both represent a vector 3, 4. As would any arrow, same length, pointing in the same direction. And those arrows are called equivalent and parallel. That's the big piece here that your book was missing. Equivalent and parallel. They're going to ask us to talk about some parallel vectors, and we need to know that they're being equivalent means that they are parallel. You know, they're the same vector, they're just located in a new spot. If we took vector OP and moved it over, it would be parallel and exactly the same length as vector RS. So equivalent and parallel vectors. Now this little piece here adds a little bit to this, and that is what I was talking about before. It represents a vector. It's not the actual motion itself, it's just a representation of that. So while an arrow represents a vector, it is not the vector itself, since each vector can be represented by an infinite number of equivalent arrows. Still, it's hard to avoid referring to the vector PQ in practice, and we do that anyway to be able to talk about them. So when we say the vector u equals vector PQ, we really mean the vector u is represented by the vector PQ in the picture. It's a representation of the vector. So how do we know that they're the same? How do we know that they're parallel? Well, if an arrow has initial point x sub 1, y sub 1, and a terminal point x sub 2, y sub 2, it represents the vector that can be found by finding the difference between the horizontal components and the difference between the vertical components. And please don't flip the page after you're done with this, because we're going to go back up to OP and RS and see that those are, in fact, meeting that head minus tail rule. Without us having to check the length, we want to see, do they represent the same vector? So back up here we go for vector RS. And again, that's the representation of this component form. And then we just quickly do a little subtraction and say, well, if it's RS, then this is the tail, and this is the head. The one with the arrow pointing on it is actually going to be the head. And it was the head minus tail rule. So negative 1 minus a negative 4 would be negative 1 plus 4. And then head minus tail for the y's, 6 minus 2 is 4. And what we want to show is it has the exact same component form as OP. Well, 3 minus 0 is 3, and 4 minus 0 is 4. Now, what's important about that sometimes gets missed when you first start vectors is you always have to do head minus tail. That direction stays the same every time. You can't just arbitrarily say, you know what, I'm going to do 0 minus 3 and 0 minus 4. Head minus tail every time. So now we can see, yeah, they match. Just by doing a little bit of subtraction here, we see that the component forms for those two vectors are exactly the same. So now, example 1 has us do that again, and this time I'm going to write down all the little baby steps and stuff so we have all of that in the notes. So, show that the arrow from R at negative 4, 2 to S at negative 1, 6 is equivalent to the arrow from P at 2, negative 1 to Q at 5, 3. So, for vector RS, we have to remember head minus tail. So I take a look at it, and you always have it labeled properly here as well. Notice that my vector half arrow is pointing towards S. So it'll be negative 1 minus a negative 4. And then we'll have 6 minus 2. So negative 1 plus 4 will be 3. And 6 minus 2 would be 4. So there's my representation. Component form. And then PQ has to be labeled that way because Q has the head, which is the arrow. And we would need 5 minus 2 and 3 minus a negative 1 to get our component form. 5 minus 2 is 3, and 3 minus a negative 1 is 4. So they're equivalent and parallel. Same vector, located in a new position, but definitely the direction is the same because we see that they'd both be 0, 0 to 3, 4 if we started at the 0, the origin for a vector. So now, exploration 1 says vector archery. And we've got, see how well you can direct arrows in a plane using vector information and the head minus tail rule. Again, the big deal here is it has to be head minus tail. You can't just decide to go from the other direction. It doesn't work that way. So vectors, the direction we have is really important. An arrow has an initial point at 2, 3. So that means we're going to start down here at 2, 3 and a terminal point up here at 7, 5. So the two names for those, initial and then terminal. Initial is going to be your head. Terminal is going to be your tail. What vector does it represent? All right, well, I need head minus tail. Oh, and we don't have anything to label it. They didn't give us a vector RS or anything like that. So 7 minus 2 is 5, and 5 minus 3 is 2. So there it is in component form, 5, 2. Now number 2 says, let's start moving some stuff. An arrow has that initial point at 3, 5, and it's represented by the vector negative 3, 6. What is the terminal point? So I don't know what this piece is, but I know it's some xy. I mean, that I know. So if we take x minus 3, we're supposed to get negative 3. I mean, they're giving us the answer. It works out to be negative 3, 6. And if we take y minus 5, it's supposed to come out to be 6. So we've got some pretty basic algebra there to figure out where that terminal point is. So we'd add 3 to both sides, add 5 to both sides. And then we'd make sure to write this one as an ordered pair because this wasn't about finding the vector in the component form. They gave us that. This was about finding that terminal point. So ordered pair. Number 3. If P is the point 4, -3, and our vector is PQ, well, that just told me that this is the tail at P. And again, they're giving me the answer. They're telling me that our vector PQ is represented by 2, -4, and we're supposed to find that terminal point again. So same kind of math that we just did. We don't know what it is, so we make it some kind of XY over here for Q, and we do a little algebra. And again, we stop and ask ourselves, okay, was this vector? Is this a point? And this was our head, so our terminal point. So we use an ordered pair notation for our 6 and -7. Why don't you go ahead and give number 4 a try, because I know you were a little bit ahead of me on this last one anyway. So go ahead and try number 4. How's everybody doing? So far, so good? Okay, just remember that the direction is important here. Head minus tail. And a little algebra. Some people get to the point where they're like, oh, I can find it without having to write down any algebra for this. Sure, if you can do that, great. The magnitude. That's the distance, the length of that arrow. So the magnitude, or norm, most books go with magnitude, hardly any of them talk about it as the norm, of a vector v is also called the absolute value of b, so it is usually denoted by, this is not true, this book denotes it by one set of absolute value bars. 20 years ago, you would never find that for magnitude. Math textbooks tend to use 2 bars on each side to talk about magnitude, and that's because we want those concepts of magnitude and absolute value to be 2 separate things. But with vectors, it actually is going to give you the same value, you know, whether or not you're talking about absolute value or the magnitude. So most of the time you're going to catch me doing this because that's the way it was always written until they decided that it costs too much to have somebody put 2 lines on each side instead of 1 when they made the new books. So that's really the reason why they went to this 1 notation, because absolute value was already on computers. They didn't need anything special for that. So it's a non-negative real number, not a vector, because it's length. You know, and the distance formula will always pop out positive answers. So magnitude, if v is represented by an arrow from the ordered pair x1, y sub 1 to x sub 2, y sub 2, then to find the distance, basically this is just a distance formula right here. I mean, that's it. So to find that magnitude, if we have the component form AB, that means that our points were 0, 0, and AB. So if you put that into the distance formula, it goes a little bit easier, because then you'll just have the square root of a squared plus b squared. Because a minus 0 is a, and b minus 0 is b. So magnitude is one part of our vector, and then we'll start talking about the distance, because that's another part of it. So finding magnitude of a vector, and they're representing this little PQ up here. Find the magnitude of vector v represented by vector PQ, where p is the ordered pair -3, 4, and q is -5, 2. So if I want the magnitude of vector v, I have to think distance formula. Big square root, find the difference between the two x coordinates. So -3 minus a -5 squared plus 4 minus 2 squared. So -3 minus a -5 would be -3 plus 5, which would give us 2 squared plus 2 squared. Square root of 4 plus 4, square root of 8. And we could simplify that, square root of 4, square root of 2, 2 square roots of 2, or give it to them as a decimal, punching in on a calculator the square root of 8. But most of the time, unless it's a word problem, we would just stop and leave our perfect solution there of 2 square roots of 2. So the magnitude of v is really just using the distance formula. It's the length of the arrow. Again, it's just a representation of that vector, the length of the arrow that gives you that magnitude piece. So now, little vector operations, some basics. The algebra of vectors sometimes involves working with vectors and numbers at the same time. You want to see how two vectors act together to do something. And this is where you were working with these things in 9th grade science. So these numbers are referred to as scalars. And we have talked about scalars before. When we did matrices, we talked about taking a scalar and multiplying all of our elements in the matrix by a scalar. It's the same thing here. The two most basic algebraic operations involving vectors are vector addition and scalar multiplication. Now, what's important about this, bless you, so that we have enough background to do the homework, is that we understand that scalars are parallel to each other. We're not changing the direction, it's just like a stretch. If we had a number in front of our A, H, and K formulas this year, we knew that if A was a number bigger than 1, it was going to be a vertical stretch. Same thing here. If you have a number bigger than 1 in the front of a vector, you're stretching it. And if you have a fraction between 0 and 1, then you're going to be compressing it and making it shorter. So scalars definitely going to be parallel. So definition, vector addition and scalar multiplication. This will not be shocking. It says if you have a vector in component form, u sub 1, u sub 2, and another vector in component form, v sub 1, v sub 2, they're vectors and let k be some real number, a scalar. So the sum or resultant, usually with vectors we talk about resultant vectors, not sums and those types of things, so resultant vectors. The sum or resultant of the vector uv is the vector you get by, well, if you're doing addition, you just add the two x components together and you add the two y components together. That's it. That's vector addition. If you have the product of a scalar, you just multiply both of those components by that scalar. So it's not tough math. You just have to know that's how it's done. So in the tail-to-head representation, which is what we've been looking at for our arrows, the standard representation of u points from the origin, u sub 1, u sub 2. So the arrow from the origin, u sub 1, u sub 2, to u sub 1 plus v sub 1, u sub 2 plus v sub 2, represents v, as we can verify by the head minus tail rule. And the arrow from the origin to that new point that we have there, the terminal point, represents the vectors u plus v. So that's in English. It's better with a picture. With a picture, here's what we're saying. If you have vector u and you line up vector v to add it, you have to do tail, head, tail, head. If you line it up that way, from the first tail to the final head will be the resultant vector. That's how we can add them. Most geometry books and most of the vectors and matrices books that you have in college use the parallelogram representation instead and say, hey, if we just put the two tails right here at the origin, then make a parallelogram out of those two vectors, the diagonal will always be the resultant vector. And either one of these works. So In the parallelogram representation, it's like I said, I think your geometry book even has that one in it. The standard representations of u and v determine a parallelogram, the diagonal of which is the standard representation of u plus v. So we can draw it, is what we're saying. We have a couple of methods that we can use here to draw those vectors. Thank you. Most common one would be the parallelogram one because that's the most basic. All right, next up. The product ku of a scalar k and the vector u can be represented by a stretch or a shrink, like I was talking about. Think of it as if it's a when we're doing our a, h, and k formulas. And if k is greater than 0, then ku definitely points in the same direction. It's just a stretch. And if k is less than 0, it points in the opposite direction. So if we have a negative, we can do that, turns that direction around. But notice these are parallel. And I keep bringing that up because in your homework, they're going to say, here's a vector. Is this one parallel? And you just need to look and see, did they multiply by a scalar? If they multiplied by a scalar, then they're parallel with each other. And possibly at the test at the end of the year, we will ask you, are these parallel vectors? In which case, you want to remember, if you multiply by a scalar, yes, they're going to be parallel. That's how we get them. So down here, we're going to do some basic vector operations. Let u equal component form -1, 3 and v component form 4, 7. Let's just play with them a little bit, So find the component form of the following vectors, the resultant vector, u plus v. So we need to take the x components and add them together, the y components and add them together. Well, that's not the toughest math we've done all year, is it? But that's what you do. It's just like matrices, We had to learn how to add matrices, to add the entries. Same thing here. This one is just multiplying by a scalar. So we're going to take 3 times vector u. So you go up and look for the labels. And you remember, well, all that means is multiply them both by that. Scalars. Got it. Oh my, a challenge problem. Scalars and addition. Well, just take your time. Give it a try. Bless you. So far, so good. How'd you do in the challenge problem? All right, so both are scalars there and our addition operations. And yeah, you'll have some of those in the homework as well, just some basic vector operations. Now, to represent it, they have a couple of pictures here to show us. We've got our u at -1, 3 and our v at 4, 7. And if you want the resultant vector, again, the two things we could do, we could form a parallelogram. If I can get blue to work here. And draw that diagonal in. That would be a representation of it. But the component form with the numbers, it makes that a lot easier. The second one over there is going to represent 3u. And that's just by taking our vector, multiplying by a scalar of 3, boom, you've got it. It's 3 times as long as it was when you started, which is not a shocker. So, vector notation, as I said earlier, that was another one of the vector notations that once they started wanting to type them up into textbooks, they decided, well, we already have arrows on our computers, but we don't necessarily have vectors. So this is actually what a vector, should look like. Write it either way now because, like I said, most books, older books will use that vector notation, but new books will definitely go with array instead. So We also have the notations, component form AB, which we've been working with, and it's great. You know, component form is really quick to work with. But we also have this A times I plus B times J. And you wonder, what on earth are they talking about? Well, that is called standard form. They'll mention that again as we go through here. But you'd take A times 1, 0 plus B times 0, 1. So this 1, 0 vector is really I, and this 0, 1 vector is really J. So it's a way to break those apart and have two different representations for vectors. So the second one, those are designed to convey the idea that a single vector V has two separate components, whether or not you're using the component form or you're using this representation over here with vectors I and J. So this is what makes a two-dimensional vector two-dimensional, and it can represent three-dimensional, so we do see that there. Like I said, mostly we're going to stick with the two-dimensional for what we're doing. Scientists stick to the component form. Again, it looks like a smushed less than and greater than symbol there for higher dimensions than 3. And we use it a ton for 2 dimensions as well. So now, we mentioned how one of our objectives was to understand a unit vector. A unit vector is a vector that goes in the exact same direction as the vector that we have, but is only 1 unit long. So the length is what we're really caring about here. Now, a vector U with a length where the magnitude is 1 is a unit vector. So if V is not the 0 vector at 0, 0, this is how we're going to find it. U equals vector V divided by its magnitude. But we want to use this in component form. So in component form, what we'll do is we'll split this up so that it's a scalar. And we'll use it as a scalar times our component form for our vector V. So that is a unit vector in the direction of V. Again, if they ask you to write parallel vectors, this is another thing that's really useful for parallel vectors, because you can take whatever vector they give you and make it a unit vector, and then multiply it by a scalar, and you'll know you will have kept the direction of the vector. You're just changing that magnitude. So unit vectors provide a way to represent the direction of a non-zero vector. Any vector in the direction of V, or the opposite direction, is a scalar multiple of this unit vector U. So parallel vectors, like I said, this book doesn't really hit them hard enough. Example 4, finding a unit vector. Okay, so find a unit vector in the direction of V, which is the vector -3, 2, and then we'll verify that it has a length of 1. So I think about the formula. And I realize I'm going to have to find the magnitude of V. I mean, that's part of being able to do the unit vector. So if it's a unit vector in the direction of -3, 2, that means it started at 0, 0. So I can just use or square root of u squared plus b squared, whatever you want to use in there. But because a minus 0 is a and b minus 0 is b, I can just shorten it up. -3 squared is 9, and 2 squared is 4, and 9 plus 4 is 13. So I need 1 over the square root of 13 times the original vector itself in component form. And we are not going to rationalize the denominator or anything like that. We don't do that with vectors. But what we do need to do is verify that, in fact, the length of that vector is now going to be 1. 1 unit for a unit vector. So now I have my new vector, and I want the square root of since it's the vector in the component form, again, my tail would have been at 0, 0. So it's going to be negative 3 over the square root of 13 squared plus 2 over the square root of 13 squared. So this is how we verify. Well, let's see. Negative 3 squared is 9. Square root of 13 squared is going to be 13. 2 squared is 4. Square root of 13 squared is 13. Well, that's the square root of 13 thirteenths, which means, yes, we did it, because it's 1 unit long. And there it is. So again, 1 over the magnitude times the vector in component form. Using 1 over the magnitude of v as a scalar will get you a unit vector. So let's see, I suppose I better circle our two answers here. So the first one was finding that, and then the second one was the verification that in fact, yeah, it comes out to 1. We get a unit vector there. Now, the two unit vectors that they mentioned earlier is I and j, 1, 0 and 0, 1. Those are the standard unit vectors. We're supposed to use component form and standard unit vectors interchangeably, but most mathematicians really like component form better. There's certain math that you can do if you have it in standard form that, yes, will help you out. So we need to know it's there, and we need to know its representation. Any vector v can be written as an expression in terms of those standard unit vectors. So if we have a vector v represented by the components a and b, we could write that as a0 plus 0b, and then say, you know what, I'm going to take those out as a scalar so that I can represent this as a standard unit vector, ai plus bj. And there it is. So we can do it. We don't do it a whole lot. Down here in the Christmas colors, here the vector v is component form ab and is expressed as a linear combination ai plus bj of the vectors I and j. Pardon me. The scalars a and b are the horizontal and vertical components, respectively, of the vector v. Gosh, maybe in your homework they might give you an example of when it's easier to work with these as a linear combination, but with just doing the two sections, probably not. We just need to know they're there, and that there are times when it is easier to use the ai plus bj standard representation than it is to use the component form. But most of our work is with the component form. So here, the vector v is equal to ai plus bj. So if we broke it down and just had the horizontal form and just had the vertical form, we could create a rectangle and we could put our component form ab in there. Now, the reason to do that is so that we can start talking about direction. I mean, we want to know what is the direction of our vector, because they have both magnitude and direction. So I started thinking, if I need to know this side, how's that going to work? And if I need to know this angle, how's that going to work? And it's basic trig of SOHCAHTOA. I mean, that's what we're talking about here. Because if this is our vector, we can use that as our hypotenuse in a triangle, and we can get the components that we need, the horizontal and the vertical. So now we talk direction. The direction of vector v is the direction angle. And up there in the drawing, it would have been the angle theta that v makes with the positive x-axis. Using trigonometry, we see that the horizontal component of v would be magnitude of v cosine of theta. All right, well, how do we get that? Well, here's theta. We're talking about this side, so this is usually our x. And then we have our y component here. And v would be represented by the magnitude of v, because that would be our distance. So if we want to figure out what the x-coordinate is, we'd use adjacent over hypotenuse. Equals the cosine of theta. But that's not what we want. We want the x piece here. I mean, we were looking to solve for x, so we'd multiply both sides by the magnitude of v. Now, usually what we're doing is using this to find theta. We're using this to find that direction. But there are times when we use it to find that length for x as well. So, magnitude of v, cosine of theta. The vertical component, magnitude of v, sine of theta. Solving for these is called resolving the vector. Now we should kind of be used to this, because remember when we did our unit circle, the x was always the cosine and the y was always the sine. So think that way as you're working through these. You've got this new magnitude piece, but that's just the length of the hypotenuse in our triangle. Alrighty, so when you want to resolve a vector, if v has direction angle theta, the components of v can be computed using the formula. Magnitude of v cosine of theta for the x-coordinate, magnitude of v sine of theta for the y-coordinate. From the formula above, it follows that the unit vector in the direction of v is, well, take a look at our v over the magnitude, which again, in component form, we used like a scalar. That's going to be cosine of theta and sine of theta. So, example 5 says, let's start finding some components here. Finding the components of a vector. Find the components of vector v with direction angle 115 degrees and magnitude 6 using no technology except to approximate the exact trigonometric solution. So, what they're saying is what we already know, which is show all of your steps and then just grab a calculator at the last second to show what you get. So, horizontal component is supposed to be magnitude of v, cosine of theta, and the vertical component, magnitude of v, sine of theta. Well, both of those require the magnitude, which is okay because they gave us that. Right there. And they gave us the degrees that we're supposed to use. So we'd get 6 cosine of 115 degrees and 6 sine of 115 degrees. And because they made a really big deal out of it, we're going to write it as component form 6 cosine of 115 degrees, 6 sine of 115 degrees. So that's what it would be exact. But if we're going to do math with it, we're probably going to have to punch it into a calculator at some point. So this is a good time to stop and say, what would we get? Well, first, we have to make sure that we're back in the degree mode on our calculators. And mine is right there. And then we need 6 cosine of 115. And 6 sine of 115. So there they are. There are the components, horizontal and vertical, and we would round those to 3 decimal places. But like I said, with these directions, they made it pretty clear. They definitely wanted to see this before we wrote down our negative 2.536 and 5.438. So now, something here has to be a little harder than this, right? And what's going to be a little bit harder is when we have to find the direction angle. And the reason that's going to be a little more difficult, not a lot, we'll think of it a little bit differently, is because remember, when you're working backwards to find those angles, you have to think about the PVR. Do you remember the PVR? So it's our knuckle thing, sine, cosine, tangent. So when we have to find that angle, usually we'll just use a little bit more creative way of figuring out what it is. But don't forget that the PVR is the reason why we have to use those creative methods. So this one says, finding the direction angle of a vector, we want to find the magnitude and direction of these two vectors that they have in the picture over here. And we have u is 3, 2. All right. Well, magnitude first. I mean, should be able to do that one. Whoops, green. Why did I grab green? Because again, in this component form, the tail is 0, 0. So there we've got our little square root of 13 for our magnitude. Now we need the direction. So if we need the direction right here, we could use either magnitude cosine of theta equals x, or magnitude cosine of, or sine of theta equals y. I think I'm going to just stick with cosine here. So our magnitude times the cosine of, and this time they've got a little alpha sitting in there, has to come out to 3, because that's how you get the x-coordinate. Well, we know the magnitude already. That's the square root of 13. So if I want to figure out what the angle is, what alpha is, I'm going to have to do the inverse cosine of square root of 13ths. So inverse cosine of 3 over the square root of 13 to get alpha. So if I'm using the inverses, I need to think for a second, am I in the PVR for cosine? Yeah, up here in first quadrant, we're totally fine. That fits cosine and sine. Not going to make a difference. So inverse All right. So you'll be able to do most of that. Sorry, I should have put my little timer on. I thought I could get through it today. So we will have to start there tomorrow with example 6. Assignments on Schoology as well, so you can get it from there. You don't have to wait around and write it down.